Hey everyone, tough concavity problem ahead. This is example 7 in Stewart's section 4.3 on concavity. Let's jump in. We're given the function f of x equals x to the 2/3 times 6 minus x to the 1/3. The reason they give us that product is so that we can easily identify the zeros of f as being 0 and 6. So that's where we know that the graph touches the x-axis. It's very nice to know that. You might also notice that if we plug in 0, we get 0. So it's nice for them to spell it out for us like that. Now that said, for differentiation purposes, it's easier if we actually write it like this. X squared times 6 minus x raised to the 1/3. Right? Put the x squared inside the 1/3 and then multiply it through and you get 6x squared minus x cubed all to the 1/3 power. Okay. So when we take the derivative, we're going to get 1/3 6x squared minus x cubed to the negative 2/3 times, because we're doing the chain rule, 12x minus 3x squared. But while it's good to be able to take this derivative, it's also important to be able to identify the zeros, right, in the numerator, as well as the values that will give us 0 in the denominator, because that's not allowed. So it turns out you can simplify this expression to be this, right? That would be a great exercise to check. Remember, you can pull out a certain square or quadratic power of x from the 1/3 power. Just remember to take the third root of it when you do so. Anyway, we let this equal 0, and we can see that this equals 0 at x equals 4. Also, f prime does not exist at x equals 0 and 6. Okay, very important to realize that. Otherwise, if you don't notice that it's 0 in the denominator at those 2 points, you're going to get thrown off. It'll mess up your entire graph and your entire approach. Make that D&E a little bit nicer. There we go. Okay, now, before we draw the chart, we're just going to take the second derivative. And this is quite a pain, actually. So I'm just going to go ahead and tell you what it is after a lot of simplification, right? It's not all that bad if you simplify the first derivative, but after a lot of simplification, you can get negative 8 over x to the 4/3 times 6 minus x to the 5/3, right? And we want to let that equal 0. Well, you might notice that does not equal 0. The numerator never equals 0, so the whole expression never equals 0 for any x value. You can't divide by something and get 0. Maybe I'll put a comma, but note again that f prime does not exist at x equals 0 or 6, right? And again, that should be kind of clear because the first derivative didn't exist there either. So of course the second derivative would not either. Like that's just a given, right? If a function doesn't exist at an x value, then its derivative won't. So anyway, now we have all of these, so now we can create our derivative chart. And we've got a couple of points to consider, a couple of x values, right? We've got x equals 0 for both the first and second derivatives. We've got x equals 4 for the first derivative, and we have x equals 6 for both the first and second derivatives, right? Now remember, these are critical numbers. Even though the derivative or second derivative doesn't equal 0 at them, they don't exist. So they're still critical numbers. We still have to consider them. Anyway, we plug in values. This is a little bit tricky. It's best to look at whether the numerator is positive and whether the denominator is positive. So remember, we're looking at this function here to figure out these values, okay? So we plug in a negative number here. Well, the numerator is obviously going to be positive, this will be negative, and this is always going to be positive because it's raised to an even power, right? Something raised to the 1/3 power squared. Okay, so we have a positive, let's see, divided by a negative times a positive. That's going to give us a negative. Plug in a value from 0 to 4. Well, the top is still going to be positive, and the bottom is also going to be positive. So we actually have that. Function's increasing there. Now, if we plug in, let's say, 5, top is negative and the bottom is positive. So the whole thing's going to be negative because, negative divided by positive is negative. Last but not least, anything above 6, top is negative, and the bottom is, of course, positive. So once again, we have negative. Just want to point out that we have a negative derivative here, then a 0, then another negative. That can happen. Okay. Anyway, if you plug stuff into the second derivative, note that the top is always negative, and that this term is always positive because, again, it's x to the 1/3 raised to the 4th. So it all comes down to what's happening here. And when you plug in a negative number, this term right here is positive. So the whole thing is negative. Similarly, if you plug in a value from 0 to 6, let's say, 1, top is, of course, negative. This term is positive. And then the bottom term is positive, making the whole fraction negative. And then if you plug in a value bigger than 6, well, the top is negative, this value is positive, and then this value becomes negative. So actually, you have a positive second derivative there. So you can say, okay, well, f is increasing on 0 to 4 and decreasing everywhere else, basically, but you should be more specific than that. On negative infinity to 0, union 4 to 6, union 6 to infinity. Do not write 4 to infinity. It's not increasing or decreasing at 6. It's not doing either of those things. The derivative doesn't exist there. We'll see why in a sec. Okay, f is concave up on 6 to infinity and concave down. Again, everywhere else, but let's be a little more specific than that. Negative infinity to 0, union 0 to 6. Don't say it's concave down on 0 because it's not. Second derivative does not exist there. Okay? So now in this little bit of space, let's try to draw a graph, right? I'm not sure how obvious this is, but we know that we have a double negative right there. So we've got this sort of curve. We also know, thanks to the way the function was stated originally here, that we have zeros at the origin and at x equals 6. So it turns out we've got a curve coming down like this. Then something kind of weird happens. We actually have a cusp where we start going up like this. It's maybe even a little bit more pronounced than that. It sort of goes up to here where we hit 4, and then we start to come down again. And then we know, again, that we hit 0 there. So this is not exactly symmetric. That's not exactly a symmetric curve. And then, weirdly, we have this curve. So we see right here, this is a vertical tangent line right here. So kind of a weird thing, right? We have cusps right here and a vertical tangent line right here. So that's why our derivatives don't exist. So that's what you've got. Very hard problem. I would never give you this on a quiz or an exam, but I do think it's a good, tough example. And if you can do this, then you can do anything. Thanks for watching.